All right, to determine percent composition, if you have a formula given to you, you're going to take the number of atoms of that element multiplied by the atomic mass of that element, which comes from the periodic table, divided by the formula mass of the entire compound. Again, from the periodic table, everything added together. So if I ask you to find the percent of hydrogen in water, then you would take first of all, what's the formula for water? H2O. So H2O. So you take 2 atoms of hydrogen. Each atom of hydrogen is 1.01 grams per mole, divided by 18.02, which is what? Formula mass. Have we calculated that before? Okay. Times 100. And really, you don't need to put the percent there. I'm not sure why I did that. That's unlike me, to be honest with you. Not sure why I did that. I'm almost thinking that percent is a typo and it should have been over here. That would be more what I would have done, because it's simply multiplied by 100. So 2 times 1.01 divided by 18.02 times 100. Do that. Plug it in your calculator. And use proper significant figures. So 1.01 is 3 significant digits. So do you get 11.2%? So 11.2% hydrogen. Now, if I ask for simply percent composition of a compound, that means calculate the percent of each element. So if I say to you, find the percent composition of a compound, then that means calculate the percent of each element. Otherwise, just do the element I'm telling you to do. So like in this situation, it said just find percent of who? Of hydrogen. So you're just doing hydrogen in this other one, in this one. Okay? All right, let's do some practice found on the next page. So the question says, what is the percent composition of aluminum sulfate? What is that going to be? Is that just one of them or all of them? All of them. So you're going to have basically 3 problems. Percent of aluminum equals percent of sulfur equals percent of oxygen equals. The reason I'm setting it up this way is because we can actually do the setup for each problem at the same time and then just run them in your calculator. So how many aluminums do we have? Times is it 26.98 or 26.99? I can't remember. Okay, so 26.98 divided by, we don't know that yet, we'll figure it out in a minute, what's percent of sulfur? 3 times what? Good, divided by, and oxygen is? How many? 12 times 16 divided by. Now, do you realize what you have by doing that? What do you have? What can you use this information for? This, this, and this. What can you use that for? Is that the molar mass? Isn't that how we calculate molar mass? 2 times 26.98 plus 3 times 32.107 plus 12 times 16. So just multiply those and add them together, and that tells you the bottom number. If you want to do a little side problem, that's fine too. Do you get 342.17? So 342.17 goes on the bottom for each one of these, times 100, times 100, times 100. And then how many significant figures will each one of these have? 4. Good. So plug it in. So what is my first answer? Good. So that's percent aluminum. All right, somebody tell me the second answer. 28.12% sulfur. All right, somebody tell me the third answer. Percent oxygen. Very good. Very good. And notice it said percent composition, so that means everything. That's what it wanted. When it says percent composition, that means everything. Now, notice what I did not do. What I did not do is do one or two of these and then subtract from what? 100. Don't do that, because if you mess that one up, you've messed everything up. Now, obviously, if you messed the way we did it by using this and then adding together, if you messed one of those up, you've also messed everything up. It's always a good idea to double check yourself, okay? This isn't hard stuff though. I don't think, unless you just make an absolutely silly mistake and don't know your symbols and elements, and maybe you pulled off a wrong, like you pulled off arsenic instead of aluminum or something like that, it's really not a hard thing to do. So I think most people are going to get this pretty easy if you just remember what you're doing, okay? Any questions on those? I know that's only one example of each, but I think that's pretty straightforward. All right, let's look at what empirical and molecular formulas are. So an empirical formula is the simplest formula or reduced formula. It's the simplest or reduced formula. Most ionic compounds are written in the empirical formula. Or with, however you want to say it. It's the empirical formula that you see with an ionic compound. So an example of this would be CaCl2. Can you reduce that any? Subscript-wise? No, that's in its reduced state. You cannot reduce that any at all. So that would be an empirical formula. Another one, that's an ionic compound. Another molecular formula would be CH2O. That is an empirical formula. It cannot be reduced any more than that. A molecular formula is a true formula. It represents the actual number of atoms in the compound. It's the true formula. It represents the actual number of atoms in the compound. Molecular formulas are always used for molecular compounds. And sometimes the molecular and empirical formulas are the same, such as in ionic compounds. The molecular formula is the true formula. It is the simplest formula as well. So if you look, for instance, calcium chloride, CaCl2, is that the empirical formula? Is that the simplest formula? Yes. Is that also the true formula for calcium chloride? Yeah, I mean, that is the true formula for calcium chloride, so it's also the molecular formula. In molecular compounds, though, many times the molecular formula and empirical formula are different. So here's an example of that. C6H12O6, which is glucose. That's glucose. That's your blood sugar. That would be a molecular formula. What is its empirical formula? Reduce that. CH2O. Do you see that? So is this the empirical formula for this? Does that make sense? So this is the empirical formula. That's the molecular formula. This is the true formula. Now, sometimes, as I've already said, the molecular formula and the empirical formula are the same. That, just CH2O, is formaldehyde. So simply CH2O, that's it, just CH2O, that is formaldehyde. But that is the empirical formula for glucose. Does that make sense? I know it doesn't make sense really, because you're like, how? How can that be? Well, you've got to remember the molecular formula is the expanded or the true formula. The empirical formula is the reduced. So this is the reduced of that. CH2O is the reduced of glucose, but CH2O is also its own compound. Okay? So what's the benefit of finding an empirical formula? If empirical formula is not always the true formula, what's the benefit of finding it? Well, let's go to a scenario of an unknown substance. Now, I don't watch TV, but I know I don't watch much TV, let's put it that way. I know for a while, and I don't know what popular TV is now for most people, but I know for a while, several years ago, I shouldn't say many, several years ago, crime shows were very, very popular. And I think crime shows are probably still fairly popular. So like NCSI and all the different things where they they go in, and a lot of it I think now is more like homicide stuff, but take a crime scene where there is an unknown substance. Now, people don't do what it shows you on TV. What does it show you oftentimes they'll do with an unknown white powder on TV? Stick it in their mouth. They don't do that. You don't do that. You don't, wet your finger and stick it in there and stick it in your mouth to see what it tastes like. You don't do that. It's not something you do. So what do? If they have an unknown substance, what would you do? Well, we have, as chemists and crime labs, have instrumentation that if you bring in a sample, first of all, they're going to do simple tests on it. They may see if it's soluble in water. They may see if it's soluble in alcohol. They may see if it's soluble in carbon tetrachloride, and that would help determine whether it is an ionic substance that would be soluble in water, whether it's a molecular substance that would be soluble in carbon tetrachloride. They may also check the melting point. There's several things they can do that are very simple tests that they can do, but then they also have instrumentation that you literally put the sample into this instrument, and the instrument spits out to you the percentage of element in that substance. So it's going to spit out to you, this is blank percent carbon, this is blank percent copper, this is blank percent whatever. From that percentage data, you actually can determine an empirical formula. Now, an empirical formula is not the true formula necessarily, but does that certainly narrow down your options? Would you think that would narrow down your options of what it is? Absolutely. Absolutely. And then, by knowing the empirical formula along with the other characteristics that you've determined, you can figure out what the substance is and what its actual molecular formula is. And those are things that are truly, truly done. This is something that is a real life scenario that's done. So what we are going to do is calculate empirical formulas. Now, it looks like it's this long, long process, but I've basically spit it out into little sections, and it's super simple to do it. And so here are the rules for calculating an empirical formula as well as calculating a molecular formula. So the first thing it says is if percentage of elements are given, you assume 100 grams of total compound. Now, why would we do that? Why would assuming 100 grams of compound help us? What does that automatically mean for you? If you know the percentages and you say, okay, let's assume I have 100 grams, what does that automatically tell you? How many grams of each substance you have, each of it. Does that make sense? Now, I want to tell you, true story, that step, and I don't know why I remember this, because I don't remember that many things, probably because I've repeated this story so many times is the only reason I remember it. But when I was sitting in high school chemistry class a very long time ago, I remember not remembering that. I forgot to assume 100 grams. And by not assuming 100 grams, I couldn't figure out how to do the problem. I missed that one step. So I'm telling you that so that you will not forget. Assume 100 grams if percentages are given, because then this would allow the percentages to become considered in grams. That's what that does for you. So if percentages are given, assume 100 grams, and that allows you to have grams for each of the substances. If actual masses are given, then use them. You use them, okay? The goal is to what? Start with what unit? That's my whole point here. What do you start with? What unit what must you start with? Grams. That's the goal. You must start with grams. And that's what it says. You must start with grams. And so I'm just going to put that. Must start with grams. You must start with grams. And so then it tells you to convert grams of each element to moles. Do we know how to do that? Using what? Atomic mass. Good. And then it says divide the mole quantities obtained in the previous step by the smallest mole quantity, and that is how you're getting a mole ratio. That's what you're getting. You're getting a mole ratio. Now, when we talk about a mole ratio, let me show you what I mean by that, because that's a new concept. Go back here. We have been talking about this being one atom and two atoms. Yet when we calculate the molar mass, what are we saying? 1 times 40.08. Is that what we would use to calculate the molar mass of this? Or formula mass? If I said to you calculate the molar mass of calcium, what would you use? Look on the periodic table. If you've got one. What's the molar mass of calcium? 40.08. What's the unit? Grams per 1 mole. So aren't we saying this is 1 mole? Yes. What is this? 2 moles. So is this a molar ratio? 1 mole of calcium to 2 moles of chlorine in calcium chloride? And that's what you're doing. Aren't you trying to find these subscripts to do your empirical formula? So what you're doing is finding this mole ratio. In lab this week, and I'm going to do a problem similar to that. I'm sorry I didn't help you all out for Monday's lab. But you found a molar ratio to help you with the hydrate. That's what you were finding, is a molar ratio. Those of you who had lab yesterday. What's this molar ratio? 1 to 2 to 1. Do you see that? That's what you're finding is a molar ratio, and then you'll know the formula. So it says divide the mole quantities by the smallest mole quantity to obtain the molar ratio. Then, if the numbers obtained in step 3 are whole numbers or within 1/10, everybody always asks me, well, how close does it have to be? I'm telling you, within 1/10. Then use these numbers as subscripts for the atoms and write the empirical formula. If the numbers obtained are not whole numbers, then you're going to multiply each of them by the same whole number, 2, 3, 4, whatever, until all whole numbers are obtained. Then those new multiplied numbers are the subscripts. Not to sneeze, sorry. All right. Remember, the empirical formula is the simplest formula. If you end up at the end of your problem and you have things that could be reduced, then you've got to reduce it. The empirical formula is the reduced. So if you multiply by a number that you shouldn't have multiplied by, and then you see, oh, those all could be simplified, then simplify. Okay? All right, I'm going to do one of these, and then we'll talk about molecular formula, okay? So let's skip over and do one of these. Anybody have any allergy medicine? Because I just realized I forgot mine this morning. Anybody has any? I'd love to see you after class. See me after class. Thank you. It's like I'm going to run home if I don't have some. I forgot to do it. All right. Calculate the empirical formula of a compound containing 52.14% carbon, 13.12% hydrogen, and 34.73% oxygen. So what do we have given to us? Percentages. So what's step 1? Thank you. And guys, write that down. Write it down. If you'll write it down, you'll remember. Assume 100 grams. So percentages are now in grams. That's why you're doing that. So what are we going to start with? Let me show you my setup. I think this will make it easy if you'll do my setup, okay? I know a lot of you may have done this before and you may have your way of doing it. Try this. I think it makes it simpler and it keeps it all in one row, okay? So look, watch what I'm doing, please. Carbon. How many do we have? 52.14 grams. Go to the next line. Hydrogen. How many do we have? 13.12 grams. Go to the next space. That's why I give so much space. What's the next one? 34.73 grams. Now, why did I set it up that way? Because what are you doing? What are we trying to find here? Tell me what the rule is. We're trying to find what? Convert grams to moles. What is the gram per mole for carbon? 12.01. So 12.01 grams for every 1 mole. This setup allows everything to stay in order so that when you get these numbers, you're going to just plug them right into a formula. That's why I do it this setup. What's hydrogen? 1.01 grams per 1 mole. What's oxygen? 16 grams per 1 mole. Now, do we see my setup here? So what are you ready to do for each of these? Are you ready to pick up your calculator now? All right. Now, here's the thing that I did not write in the rules, and you may need to go back and put it in the rules. Leave 4 to 5 places after decimal. No sig figs. If you start rounding here, you're going to mess yourself up. So you need to leave 4 to 5 places after the decimal at this step. Otherwise, your numbers will be off and they won't work. So do the math here. What do you get? No. Right here, you should not get 626. 4.34138. 4.34138 moles. 4.34138 moles. Keep going. What's the next one? 12.9901 moles. And then the last one? 0.63 or something like that. Like I said, at least 4 places after the decimal. At least 4 places after the decimal. Now, what do? What's the next step say? Go back and look at your steps. What's it say? Say it again. Nope. Look at the steps. Look at the rules. Look at the rules. I think it's rule 3. Here, I'll tell you which rule. Yep. No, rule 4. Divide by the smallest mole ratio. Which one, or mole quantity rather, divide by the smallest mole quantity. Which one of these numbers is the smallest? Oxygen. So everything gets divided by the smallest. Everything. Everything gets divided by the smallest. We'll make a note. Everything gets divided by smallest number of moles. Obviously, moles cancels out. And obviously, does one of them always end up being 1? Yes. Now, tell me what you get for the others. And remember, it's within a tenth. If it is within a tenth, it is that whole number. So what's carbon? 2. Do you get 2? What do you get for hydrogen? 6. And for oxygen, you get 1. Make sure you get that. All of you plug that in to make sure you get that. Are we together or not? So your last step is to what? Write the formula. So what's the formula? C2H6O. Do you see why I do it in this line format like I do? Because look, it tells you C2H6O1 and you don't put a 1. Yes or no? That make sense? All right, you do the next one. It says if a compound, and this is, I'm going by the rule, I'm not telling you what this says, but the problem, the rules say if a compound gives you actual mass, what do? Use it. Does this problem give you actual mass? Then use it. Use it. If it gives you actual mass, then you use it. Off your phone, buddy. Do you write this problem? How about I tell you? Iron is 55.85 and sulfur is 32.07. So this is your setup that you should have. All right, what did you get for the number of moles for iron? Come on, tell me, somebody. Good. And for sulfur, what'd you get? Okay. All right, divide by the smallest. That would be the 0.03. And we get 1 and what? 1.5. Do you get that? Now, it's not within 1/10 of a whole number, is it? So you have to call it what it is. If it's not within 1/10, you call it exactly what it is. Okay? If it is not within 1/10, then you call it exactly what it is. And then you say, what can I multiply 1.5 by in order to get a whole number? 2. If I multiply 1.5 by 2, that gives me 3. What I do to one of these, I have to do the other because I have to maintain the what? Ratio. I have to maintain the ratio. And so I multiply both of them by 2, and now what's my formula? Fe Come on, 2s3. Now, since you all know nomenclature, name that for me. Iron. It's not, no prefixes. We don't use prefixes in ionic. We use prefixes in molecular only. Is this a transition metal? So what does it have to have? Either an old name or Roman numerals. So what is sulfide's charge? -2. So that's 3 times -2 is a total of a -6. You must have something multiplied by 2 to give you a +6 on this side. So what must each iron be? +3. Does it make sense? So this is iron 3 sulfide. Iron 3 sulfide. Okay? And the formula, though, is Fe2S3. That's what you were trying to find. Okay? I just wanted to kind of refresh on nomenclature. Guys, you're going to have to know your ions. If you did not learn your ions and you don't know nomenclature, then what we start on Thursday is going to be murderous for you. Because we are going to be doing balancing equations, which is including information on predicting products. And I'm going to give you word equations, and you have to write the proper formula and then balance it. So you're not done with nomenclature. You're not done with it. If you don't know your ions, you're going to be hurting yourself the rest of the semester. So you've got an extra week to learn your ions, okay? So learn them. Learn your ions, okay? All right, now then, how do we do molecular formulas? So the rule for molecular formulas. The rule for molecular formulas, right here, it says the molecular formula is calculated by taking the empirical formula's subscripts and multiplying them by n. Note, one must have an empirical formula in order to calculate a molecular formula. You cannot calculate a molecular formula without an empirical formula. Okay, you can't do it. It's impossible. Let me say that again. Empirical formula you must have in order to calculate a molecular formula. Now, sometimes you have to calculate the empirical formula first and then get the molecular formula. Sometimes I give you the empirical formula, but you must have an empirical formula. And then you will use this equation to determine the molecular formula. It's the formula mass of the molecular formula divided by the formula mass of the empirical formula. I will always give the formula mass of the molecular formula. The formula mass of the molecular formula will always be given. And the answer you get will always be a whole number. It's not going to be something you have to multiply to get a whole number. It will be a whole number or within a tenth of a whole number. Okay? It will be a whole number. So again, I'm telling you, formula mass of molecular formula will always be given in the problem. Student must calculate formula mass of the empirical formula. That's what you must calculate. All right, so let's go to this problem. A compound of nitrogen and oxygen has a molar mass of 92 grams per mole. What is that? What is that number that I just gave you? Mass of which one? Empirical or molecular? Molecular. So immediately when you see that mass, you note molecular formula mass. That is the molecular formula mass. It says its empirical formula is NO2. So somebody gave you the empirical formula. Then it wants to know what is the molecular formula. So the first thing I would encourage you to do is put molecular formula equals mass of molecular formula divided by mass of empirical formula. That's your formula for calculating molecular formula. That's your equation. What was given to you in the problem? What have I already said? Which number will I always give you? The top or bottom number? I will always give you the top number. I will always give you the top number. So what is that top number? 92 grams per mole. How do you get the bottom number? You calculate it from the what? Empirical formula. Did I give you in this problem the empirical formula? Yes. So there is the empirical formula. So now calculate the mass. 1 times what? 14.01 plus 2 times 16. Where did I get that? Periodic table. And so you get 46.01 grams per mole. Where does that go? On the bottom. So 46.01 grams per mole, and I think if you can do any kind of math in your head, you know the answer. What's the answer? 2. 2. The answer is 2. What is that 2? That's what you multiply the subscripts by. That's your subscript multiplier. This is the subscript multiplier. Which subscripts? The subscripts of the what? Empirical formula. So what is the final molecular formula? N2O4. So the final answer is N2O4. That's your final answer. Yes or no? Make sense or not? Not hard? None of this is hard. It's long. It's long, but it's not difficult. It just takes time, and you have to do practice problems. You can't just do one problem and say, oh, I'll remember that, because you won't. You will not remember it. With all the material that's going to be on this test, you will not remember this if you don't practice it. You must practice daily. Do a problem daily, okay? Some of you I think are finally serious about your grade, but that's on you. If you are, you aren't. So hopefully you are. All right, 2 pages of problems, or 1 page of 2 problems, rather, not 2 pages of problems. 1 page with 2 problems. Both of these problems, you must calculate what first? Empirical formula, and then calculate what? Molecular formula. So you're calculating an empirical formula first, and then you have to calculate the molecular formula. Now, some of you don't know why, so let's talk about why. Why do you have to calculate an empirical formula first? What is the question actually asking you for? A molecular formula. It's asking you for a molecular formula. That's what it's asking for. It's asking for a molecular formula. But what's the rule for calculating a molecular formula? You cannot do it without an empirical formula. You cannot do it without an empirical formula. So first you must find the empirical formula. So I'm going to make a little note here for this page. First, find empirical formula. If given, use it. Then find molecular formula. When percentages are given, what's your first step? Assume 100 grams. So assume 100 grams. So I'm going to do the first one with you, and then I'm going to let you do the second one, boss, and then we'll check it, okay? So assume 100 grams. So if we, yes. Brighter? Maybe. Let's see. Is that better? No, that's good. Okay, good. Thank you. All right, so assume 100 grams. All right, now, what does that tell us? If we assume 100 grams, what does that tell us? How many grams of carbon do we have? 26.7 grams. So go ahead. If you know what you're doing, keep going. I'm going to just talk it out while I'm doing it. So carbon, we have 26.7 grams. Hydrogen, I have 2.2 grams. Oxygen, I have 71.1 grams. I go to my periodic table. How many grams are in 1 mole of carbon? 12.01 grams for every 1 mole. So grams cancel. Hydrogen is what? 1.01 grams for every 1 mole. Grams cancel. And oxygen is what? 16.00 grams for every 1 mole. So run those numbers on your calculator. On carbon, do you get 2.2231? Talk to me. So 2.2231 moles for carbon. On hydrogen, do you get 2.1782? Anybody get that? What do you get for oxygen? Good job. 4.44375 moles. Okay. Which one of these is the smallest? Hydrogen. So we're going to divide everything by 2.1782 moles. So moles cancel every time. That means this one is 1, yes or no? And then what is 2.2231 divided by 2.1782? Is it within a tenth also of being 1? And then this one is what? 2. So do we have a formula? What's the answer? CH what? O2. That is what? Not my final answer, is it? What is that? I mean, it might be my final answer, but I don't know that that's my final answer yet. Who is this? This is the empirical formula. This is the empirical formula. That's what that is. Now what do we do? Calculate N. Now we calculate N. N equals the mass of molecular formula divided by the mass of the empirical formula. What is the mass of the molecular formula? It's what I gave you in the problem. What is it? So 90.04 grams per mole. You have to calculate 12.01 plus 1.01 plus 2 times 16, which is, what is it? 45.02 grams per mole. What's that equal? 2. So what is N? N is 2. But you're still not done yet. What's my last step? Multiply that 2 by the empirical formula subscript. So what's my final answer? C2H2O4. Yes or no? All right, you do the next one by yourself. You do the next one. Did everyone sign in? All right, what do you get for carbon? Come on, somebody tell me. 4.1049? Yay or nay? Don't you like that yay or nay? All in favor? Y'all never done that before? You ever been to a business meeting of some form? All in favor? Come on, all in favor? Yay! Opposing? Nah, it's the, you know what that is. It's the donkeys, right? Just teasing, just teasing, just teasing. Okay. All right. So, hydrogen, what do we have for hydrogen? 6.83168. Actually, lots of times they'll go, hey, they'll do that. Or I. Okay, and oxygen? 2 point what? 7375? Yes or no? All right. Okay, now What's our next step? Divide by the smallest. So which one of these is the smallest? Oxygen. So everybody gets divided by 2.7375 moles. Sorry, thank you. 2.7375 moles. Obviously, that one's 1. What do we get for carbon? 1.5. Does it round to within a tenth of being a whole number? Yes or no? No, it does not round to being a whole number. Guys, you've got to remember that. It has to be within a tenth. It has to be really close. It has to be really close. What is it? I don't have my calculator today. Tell me what you actually get on your calculator. Say it louder. 1.499, right? Okay, what do you get on your calculator for this one? 2.499? Okay. So that's close to 1/2. That's way within a tenth. That's within 100th. Okay, this is within 100th, the being 2.5. Which means, what are we going to multiply these by? 2. So multiply everything by the same number. That keeps the ratio the same. So then what do we get up here for the top one? 3, 5, and 2. So C3H5O2 equals what? Empirical formula. N equals, what goes on top?
46.
Where did that come from? Say it. The problem. So 146 grams per mole given in problem. I'm going to repeat myself 10 times on that because that's what you'll forget. You'll be like, where did that number come from? I don't know where that came from. It's in the problem. I give you the top number. It's in the problem. Now, what do you have to do to get this bottom number? Find the mass of this. So this mass goes down there. So 3 times 12.01. What do you get? Tell me again. I'm sorry, do the whole thing. What's the whole answer? 73.08 grams per mole. That's what I got, 73.08 grams per mole. This is, let me tell you why I got that if you didn't. This is 12.01, so this is 12.01 times 3 plus 5 times 1.01 plus 2 times 16. Now, what do you get? 2. And that will be a whole number. If you don't get a whole number there, then you've got something wrong. That's how you'll know you have something wrong. If you don't get a whole number there, that means you've got something wrong. So then, what do we do with that? We're still not done. What do we do with this? Multiply this. So multiply subscripts by this number. And so see what? Keep going. And that is your final answer. Yes or no? Okay? Questions on these? All right, those problems are the last problems on this homework. So my suggestion to you is to get this homework done today so that it's done. Even though I moved the due date, get it done today. That would be reinforcing you on what we've done today, okay? All right, bring your notes on Thursday. Listen to me carefully on this, guys. Listen to me. Sit down for a minute. I got minutes. Give me my minutes. Listen to me. I want to show you something. actually, there's two things I'm going to show you, so keep your stuff out. Keep your stuff out. I'm going to talk about lab real quick. Keep your stuff out. These are the notes. These are the starting notes for next class period. This then goes into, this is just plain Jane balancing equations talking about types of reactions. The next page is doing this with words. If you don't bring notes on Thursday, it is going to be so hard for you. Please don't do that to yourself. Go print the notes out. Okay? Print the notes out. Now, real quick, let's talk about lab so that this will help you understand what you're doing in lab better. Okay? So let's talk real quick about lab. So in lab this week, you're calculating the formula of a what? What? Come on. Calculating the formula of a hydrate. You're calculating the formula of a hydrate. So what is a hydrate? That's the first thing you have to know. What is a hydrate? A hydrate is an ionic compound with water loosely attached to its structure. Many of the things you deal with in the real world are hydrates. Sugar itself is a hydrate. How do I know that? Because what happens if sugar gets a little moist? Not actually water put in it, but it's humid in your house. It clumps up. Sodium chloride is a very, very mild hydrate. Does it sometimes clump up too? What do you put in salt shakers? Rice. What does that do? So it says name hydrates the same as ionic compounds, then use the prefixes we learned for molecular compounds and the base word hydrate. SO4.5H2O. You name this first. So who is that? Copper who? Copper 2 sulfate. And then 5 is what name? Penta, and you say, instead of water, you say pentahydrate. So see copper 2, that's copper 2 sulfate pentahydrate. Does that make sense? This is not hard. It's just an extra step that you need to add. So in this case, lithium carbonate. What's the formula for lithium carbonate? Li2, hold on just a second, Li2CO3. Li2CO3. What would dihydrate be? 2H2O. So Li2CO3, 2H2O. Yes?
Maybe I'm stupid, but why do we call it hydrate?
Because the compound itself is called a hydrate. And that's just the proper name for that compound. A hydrate, by definition, is any ionic compound that has water loosely attached to its structure. So you name it by naming it as a hydrate. Okay? All right, so this one, calcium chloride. What's the formula for calcium chloride? CaCl2. Chloride's -1, calcium's +2. So CaCl2 trihydrate, 3H2O. Does that make sense? Now on this one, which iron is this? Iron 2. How do I know that? Because sulfate is what charge? Sulfate is what? -2. This is actually not right. I said this is not right at all. This is not right. Let's go backwards. Let's go backwards. Here's the name, iron 2. What is it? Fe with a +2 charge. Sulfate's -2. What should the formula be? FeSO4 what? 6H2O. 6H2O. Now let's do this one. Pretty sure that's what that was trying to do, and I messed up back then. So, what charge is sulfate? -2. What must this iron be? Positive what? +3. Has to be +3. Why does this one have to be +3? Because 2 times 3 is what? 6. 3 times 2 is 6. So now this name is what? Iron 3 sulfate dot, or I'm sorry, not dot, you don't put the dot there, hexahydrate. So there's a mistake I made however many years ago I did this. Those poor students. No, I didn't mess it up. I had it right. No, I didn't have it right. I had them flipped, didn't I? Yeah, I had them flipped. Okay? All right, does that help a little bit? All right, I will see you Thursday.
Like the board was like a little like.
That's fine. Just tell me that at the beginning of the class.
That's
and
why
I'll
you
do
saw me
that
like.
next
That's why
time.
you shake my
I
head.
wasn't. I didn't see it, honey. That's okay.
Yeah, because I was trying to get my eyes
Yeah.
to focus, and I thought it was my.
Right.
That's why you saw me. Probably saw me
I
polish
didn't,
my
honey.
glasses.
I don't pay that much attention, but that's good. I'm glad you told me. Anytime that's like that, tell me, okay?
Yeah,
I need to know that.
I thought honestly, I thought it was my eyesight because I was like.
No, let me know. Anytime it's like that, let me